All right, welcome. Today, we're diving into a really classic piece of electrical engineering, something that's just as clever as it is precise, the electro dynamometer. So let's jump right in and see what makes this thing tick.
So let me start with a question for you. We've all seen meters that use a permanent magnet to make the needle move, right? But what if you couldn't use one? How would you even begin to build an instrument to measure current or voltage? Well, that's the exact puzzle the electrodynamometer was built to solve. So what's the big idea here? What's the core innovation? Well, most common meters, the ones we call PMMC instruments, they rely on a permanent magnet to create a magnetic field. The electrodynamometer, though, does something totally different. It gets rid of the permanent magnet and replaces it with a fixed coil of wire. Basically, it creates an electromagnet. And you know what? That one little change is the secret sauce that makes all the difference.
Okay, to really get how this device works, we've got to pop the hood and see what's inside. So let's break down all the essential parts.
Here it is, a look inside. Now, it might look pretty simple at first glance, but every single one of these parts, from the fixed coil that creates the main magnetic field, to the moving coil that reacts to it, and of course the pointer and the springs that keep it all in check, each one plays an absolutely critical role. Let's zoom in on each piece.
First up, we've got the fixed coil. You can think of this as the heart of the whole instrument. This is what takes the place of that permanent magnet. It's usually split into two identical parts, and when you pass a current through it, boom, it generates a nice, stable magnetic field. This field is basically setting the stage for everything else that's about to happen.
And nestled right there between the two halves of that fixed coil is the moving coil. Now this is the part that, you guessed it, actually moves. It's attached directly to the pointer. When a current flows through this coil, it creates its own little magnetic field, and that field immediately tries to align itself with the bigger field from the fixed coil. It's kind of like how a compass needle always wants to point north. And that little rotation is what moves our pointer.
And of course, you've got the pointer and the scale. This is how we actually get our reading. The pointer is just attached to that moving coil, so as the coil turns, the pointer sweeps across the marked scale, and that gives us our final measurement. Simple enough, right?
Now, if that moving coil could just spin around freely, it wouldn't be very useful for taking a measurement, would it? That's where these little springs come in. As the moving coil rotates, these springs get wound up, and they create a counterforce that pushes back. It's like a perfectly calibrated little brake that stops the pointer at the exact right spot on the scale. So, we've met all the players. Now let's put it all together and see how this thing actually measures a current. This is where the magic really happens. The whole secret to the electrodynamometer is this. It's all about the interaction between two separate magnetic fields. I mean, think about it. If you hold two magnets near each other, you can feel them push or pull. That's pretty much exactly what's happening on a tiny, super-controlled scale inside this instrument. It's this magnetic dance that gives us the force we need. And where do these two magnetic fields come from? Well, it's pretty straightforward. One field comes from the current running through our stationary fixed coil, and the other one? It comes from the current running through our rotating, moving coil. That's it. Okay, so when these two magnetic fields interact, they create this twisting force. In engineering, we call that a torque. And here, we call it the deflecting torque, or TD for short. This is the force that actually pushes the moving coil and makes the pointer swing. Think of TD as the engine that drives the whole measurement. Now, here's where things get really cool. We can actually describe this entire physical process with a surprisingly elegant equation. So let's take a quick look at the math behind the magic. So how do we get from a bunch of electrical currents and invisible magnetic fields to a single precise number on a scale? Well, the answer is all about finding a perfect balance, a balance of forces. It's like a three-step dance. First, that deflecting torque, our TD, kicks in and gives the pointer a push. Then, as it moves, the springs push back with their own controlling torque, which we'll call TC. Finally, the pointer comes to a rest at the exact point where these two forces are in perfect equilibrium. The push equals the pushback. TD equals TC. That's our reading. So here's the equation for that deflecting torque. Now, I know, it might look a little intimidating, but it's actually simpler than it seems. TD is equal to I1 times I2 times this last bit, dm over d theta. Let's break it down. I1 is just the current in our fixed coil. I2 is the current in our moving coil. And that last part, don't worry about the calculus, it's just a term that describes how the magnetic interaction between the coils changes as the angle or theta changes. But let's simplify this even more, because here is the single most important thing to take away from that equation.
All it's really saying is that the deflecting torque, TD, is proportional to the product of the two currents. That's it. The bigger the currents, I1 and I2, the bigger the push on the pointer. Simple, right?
At the same time, the controlling torque from the springs, RTC, is even simpler. It's just proportional to the angle of deflection, theta. The further you twist the pointer, the harder the springs push back. It's a really clean, linear relationship. Okay, now for the big reveal. Let's put it all together. When the pointer stops moving, we know that TD equals TC. And since we know TD is proportional to I1 times I2, and TC is proportional to the angle theta, well, that means the final angle of the pointer is directly proportional to the product of the currents. And that, right there, is the fundamental principle that makes this entire amazing instrument work.
And this is where the design gets really versatile. Check this out. If you use it as a voltmeter, you wire the coils up in series. That means the exact same current, let's just call it I, flows through both. So our I1 and I2 are the same, which means the deflection, theta, is proportional to I squared. But if you use it as an ammeter, the currents I1 and I2 can be different, so the deflection is just proportional to their product. How cool is that?
So we have this really clever design, and it's based on some very solid physics. But what does that actually mean in the real world? Let's talk about the pros and cons of the Electro dynamometer.
The number one advantage, and this is a huge one, is that it can accurately measure both AC and DC. That's a real game changer. Plus, because it doesn't have an iron core, it's not affected by those pesky magnetic issues like hysteresis or eddy currents. All of this means it can be incredibly accurate.
But it's not perfect. There are some real downsides. Remember that I-squared relationship for voltmeters? That means the scale isn't uniform. It's all cramped together at the low end, which can make it hard to read. It also uses more power than a standard meter, it's more expensive to build, and honestly, it's pretty delicate. You definitely have to be careful not to overload.
So when you add it all up, the Electro dynamometer is a beautiful piece of engineering. It's super accurate, but it's also expensive, a bit of a power hog, and kind of fragile. And that brings us to a final thought. In our modern world, with digital displays everywhere, is there still a place for this kind of analog precision? That's a good question to think about. Thanks so much for joining me.